Today, countless humans are being replaced by computers in their working environments because they can do work more efficiently at much lower cost to businesses. One thing that gives humans the edge over computers is that they can adapt and learn according to certain trends. But with modern technology, computers are being taught to learn as well. There are many different ways of enabling a computer system to learn. Some algorithms work better for certain types of problems. In this video, I'll be explaining how perceptrons work and how they are used to create artificial neural networks. This theory is based on a simplified version of how humans learn. In the human body, there are billions of interconnected neurons. Each neuron has an input zone that consists of dendrites that receive the incoming signals from other neurons, and an output zone consisting of axon terminals that output the impulses from the conducting zone, the axon. In between the input zone and the output zone, the neuron has a trigger zone, where action potentials are initiated. And only when incoming impulses exceed the impulse threshold of the trigger zone, an impulse will be propagated to the next set of neurons. This action generates an all or none response. So if the incoming impulses aren't strong enough, an impulse won't be transmitted. The perceptron algorithm is the heart of the artificial neural network, as it plays the role of a single neuron in the neural system. In artificial neural networking, we layer a bunch of interconnected perceptrons together to form a neural net. Neural nets are used for linear classification. Linear classification is when you have to separate classes from one another by drawing a line, any line that accurately separates them. For example, you have a graph plotting points of the average speeds of cheetahs versus tortoises. To classify which points belong to the tortoise, you would draw a line separating the highest speeds from the lowest speeds. All the values below the line belong to the tortoise, and all the values above the line belong to the cheetah. The art of artificial neural networking lies in calculating the location and gradient or slope of that line. There are many different strategies of figuring out the slope and location of the line that is supposed to separate these classes. Artificial neural nets are a very common solution to linear problems. Let's break it down. Every neural network consists of at least 3 layers: an input layer, a hidden layer, and an output layer. The input layer consists of however many inputs you'd like your neural network to consist of. Each input has a level of importance, commonly referred to as the weighting. The weight of each input is adjusted after each loop or iteration of the algorithm. The sum of the inputs multiplied by their corresponding weights is then run through an activation function. The activation function has a threshold value that determines whether the output will be 1 or 0. In the case of our cheetah example, a 1 could mean that the input belongs to a cheetah, and a 0 could mean that it belongs to a tortoise. But how do we get to the stage where the computer can classify data? First, we have to teach it what the speed of a cheetah is, and what the speed of a tortoise is. This strategy is called supervised learning. Supervised learning is when you classify data for the computer to train it for unseen data sets. Small children are taught through supervised learning when they are taught the names of different farm animals, for example. The computer learns when the input's weights are adjusted. The way this is done is through a method called backpropagation of error. The error, by how far the weights were off, is calculated by comparing the computer's output value to the correct output value and distributing the amount of error across the weights. It's difficult to determine by how much our weights were off when we use a Heaviside step function, because it will always have a derivative of 0. This is why we turn to our trusty sigmoid function. The sigmoid function allows us to accurately determine the error of our weights so that we can more accurately adjust them for faster learning. The reason why it is more convenient is because it allows us to use a curve that runs between 0 and 1 instead of a sudden step. This allows us to compare the computer's actual value more accurately to our ideal output value. In our graph plotting the points of 2 classes, the line will likely not be allowed to run through the origin of the graph all the time. This is why we add a constant to our line, called the bias. The bias is interpreted as an additional input. It also has its own weight. This serves as the constant, similar to the constant in a straight line graph, y equals mx plus c, where c is a constant. Simply put, neural networks are just multiple perceptrons, each with more than one input, leading to one or more outputs that are taken in as inputs to the next layer of neurons until it reaches the final output layer. The final output of the neural network does not necessarily have to be a 1 or a 0. Multiple outputs are especially useful when it comes to computer vision and image classification, where you can have multiple possible classes. The outputs can be used to represent the probability of the image being classified as a certain class. In this video, you learned that computers can learn through a concept based on the way humans learn, called artificial neural networking. Artificial neural networks consist of minor components called perceptrons. Each perceptron has weighted inputs, a summation function that is fed into an activation function, and the activation function determines whether a 1 or 0 will be outputted. These perceptrons can be connected and layered to form a neural network that can be applied to more complex applications like image recognition.